This workshop brings together his collaborators, former PhD students, friends and colleagues. Many of them will deliver talks at this workshop, and we are looking forward for interesting talks, new results, and fruitful discussions. As the first speaker, I may announce Professor Glessow. He will speak about the mathematical research achievements of Valery Buldygin.
Well, preparing this talk, we faced several problems. First of them is that Buldygin's scientific interests are so broad, and it would be not possible to tell you everything about his achievements during this short 20 minutes talk. Second problem was that many of his co-authors are present here, and it would be almost nonsense for me to explain them what did they do in mathematics together with Buldygin. After a while, we decided maybe light should be switched off, then we'd better see the picture. Then we decided to tell something about scientific research achievements of Buldygin from this list. These are the books published by him, or either by him and his co-authors. Then we decided to avoid explaining number 2, number 3, number 4, and number 6, because of the second reason that the authors are present here as well. And at the very late moment, Khrazishvili, his co-authors in number 2, decided not to come to Kiev, and therefore I will tell you a few words about this book. Mainly, I will be concerned with the number 1 and number 6. Number 1 is my favorite book by other author, and number 5 is my favorite book written together with Buldygin, Steinbach, and Indlikofer. We hope that some presentation of his personal life will be shown at the end of this talk, and therefore I don't tell you any dates of his life. So this is the first book published by Buldygin, Convergence of Random Elements in Topological Spaces. I guess this is the extended version of his doctoral dissertation, which is second level dissertation still in Ukraine, and it was in Soviet Union. Here he considers a lot of questions, traditional questions for convergence of random elements, but in more general spaces than Banach space or Hilbert space. This topic was hot at that time, maybe 5 years before. This is 1980, and many authors dealt with this topic. So this is our main keywords in his monograph. He successfully used two principles he calls comparison and contraction principle. Comparison means, for example, in the case of random series, that if you have series of psi k and its convergence, and if you have another series of eta k and distributions of eta k are smooth as compared to the distributions of psi, smooth is explained in his book, then convergence of psi implies convergence of eta. For random variables, this also is useful, but for random elements in abstract linear spaces, this is one of the powerful tools to prove the convergence, because you don't need to deal with truncations and three Kolmogorov series, which are not easy in Banach spaces. And contraction principle, this is a particular example of comparison principle, meaning that if eta is lambda times xi, and lambda is real numbers, very general real numbers, then the convergence of xi nevertheless implies convergence of eta. So my favorite result in this book is Levy inequality for so-called F spaces. This is more general than, for example, Fréchet spaces, and may be explained as the spaces whose dual space may separate elements of F. So if Xn are independent and symmetric, and Sn, as usual, this is cumulative sums. Okay. Here it's not shown, but this is a domain or set, and this is also a set of F space, and this means all combinations x1 plus x2. So assume the series converges to the limit almost surely. Okay. Then this is what is known for the usual Levy inequality Sn bigger than x. This is an analog for Banach or F spaces. And here we have Levy inequality of this kind. So this union substitutes the supremum or maximum of sums for usual sums. And this is right-hand side of the same spirit. The well-known Levy inequality for Banach spaces with norms easily follows from this variant of this prominent inequality. I would like to tell you two stories from this book, and one of them is written on page 198. So this is about random variables and strong law of large numbers. So Bn, this is normalization, non-random normalization, and then he constructs special sequence from this original sequence B. I use this notation because of the usual notation for ordered statistics. B1, in brackets, this is minimum. Then this is the place for the first minimum. Then he defines second minimum after the first one and the place for it. In general, he defines subsequence B in this way. Oh, excuse me, and L should be here. And finally, he introduces special subsequence of integer numbers in this way. Fix C, positive, bigger than 1, real number, and find the last NL for which this subsequence does not exceed this one. Now, B and L is a non-decreasing sequence. Moreover, it is increasing sequence. And then he proves the following result. Strong law of large numbers holds if and only if it holds for these differences. And now this is much more easier to treat because in the nominator we have independent random variables, and this is much easier than sums themselves. So maybe many of you understand that this result is very close to some other known results One of them is Petrov and Martikainen. The other one is Volodin and Nagaev. This is well-known strong law of large numbers, or criteria for the strong law of large numbers, published by Martikainen and Petrov in 1977, and Volodin and Nagaev same year. It happened so that nobody knew that Buldygin published the same result, I described it here, almost the same time. So Martikainen, when I told him about this result of Buldygin, switched, saying that this theorem, not Martikainen and Petrov, but Buldygin, Martikainen, Petrov, Volodin, Nagaev theorem. So he supports my idea that this is, well, somehow joint results obtained independently by 3 teams of co-authors. By the way, the paper Volodin and Nagaev was reviewed by Martikainen. It came to the editorial board just a couple of days after Martikainen submitted his paper to probability theory and applications, and they decided to choose Martikainen as a reviewer for this paper, and he wrote a positive report, and Volodin and Nagaev appeared 3 months after Martikainen and Petrov. So this line of results goes back to Prokhorov and probably Loev, and generalize both these results for the general case. The other story appears on page 1 to 7, and this is lemma 3.71. Now we have independent symmetric random variable elements. Again, this is F space, let it be Banach space. And we consider cumulative sums. This is a norm, semi-norm, and then he proves the inequality. Again, many of you see some similarities of this result with obtained 1973 in his PhD thesis and published by Hoffmann-Jorgensen 1974 in Studia Mathematica. But, well, Hoffmann-Jorgensen published the same result in a preprint, so this date is indicated here, almost the same time. So we never discussed this Buldygin, these issues and how he estimates these coincidences, and that his name is not mentioned with respect to Martikainen and Petrov theorem or Hoffmann-Jorgensen inequality. He never mentioned, and I did not discuss, maybe he follows the strong Skorokhod point of view that there should be no discussion concerning priority in mathematical investigations. So this inequality, by the way, is mentioned, or sometimes Kahan is mentioned in relation to this inequality, and then Buldygin mentions something similar in the book by Gichman and Skorokhod, published before his PhD thesis. And I would like to explain to you shortly what does Kahan inequality mean. Kahan considers Rademacher random variables, epsilon, and random vectors. And summands xk are defined in this way in Kahan case. Then he considers infinite series and assumes for the sum we have estimate of this kind. And then he obtains this upper bound. So if we compare with Buldygin, Hoffmann, Jorgensen inequality, then so alpha is almost this probability, and then this is Kahan result, and this is Buldygin, Hoffmann, Jorgensen result. If we add S to the argument, this probability, then we obtain this additional term. Well, this inequality is not the last in this series. the most novel inequality is due to class and Nowitzki. I don't tell you anything about it. So this is a book published by Buldygin and Kharazishvili, and the title is Brun-Minkowski Inequality and its Applications. Let me explain what does Brun-Minkowski inequality mean. So everybody knows is a parametric inequality in the plane. It's written here. And A is the area of a domain in the plane, and L it's the length of the boundary of this domain. And then we have inequality of this kind. For the circle we have equality here. It can be extended to the three-dimensional case. Now this is the volume of a domain, and this is the area of the boundary. It turns out all these inequalities are particular cases of the well-known, well, in geometry and then in topology, Brun-Minkowski inequality. It's written this way. So we have two convex bodies in Rn, and V is the volume in Rn. The sum is defined in an obvious way, and then we have inequality of this kind. This is Brun-Minkowski inequality, and it is surprising how many applications of this geometrical fact exist in probability theory. So if you look at Buldygin-Kharazishvili book, you will see applications for the conditional expectation, for the proof of consistency of statistical estimators, for large deviations, and so on and so on. So it was interesting collaboration between probabilists Buldygin and function analytists Kharazishvili. Later on, this book was translated into English. This is functional methods in summation problems for random variables. The main topic in this book is to consider sums of random vectors normalized by matrices and study all types of convergence, almost sure probability, and in distribution. This also was hot topic at that time, and later on the book was translated into English. This is one of the most successful books of Buldygin, Metric Characterization of Random Variables and Random Processes. So I would not tell you much because Kazachenko is here, and the translator of this book, Zayats, is also here. They know everything about this book, and I know little. Just a couple of key words. This is Luxemburg norm. Am I correct? Luxemburg norm. And sub-Gaussian processes, estimation of suprema of Gaussian processes, of distribution of suprema of Gaussian processes, and so on and so on. This book was published by American Mathematical Society. Well, this is pseudo-regularly varying functions and generalized renewal processes. This was a result of our long-standing cooperation with German colleagues Josef Steinebach and Karl-Heinz Indlikoffer, supported by DFG. And this was interesting period in our life when we worked together and were enthusiastic about problems and solutions. So let me first explain something about functional part of this book. Lambda, this is real point. Well, first of all, f is a function, positive real-valued function. Lambda is called regular point if this limit exists as t tends to infinity. The set of all regular points is a set of regular points. Now, Karamata regular variation, it concerns the functions for which the set of regular points coincides with the whole real line. And the previous definition deals with only subsets of real line. By the way, GF, set of regular points, always is a subgroup in R. So if you are interested of examples of such functions, and I can provide one, it is very simple and obvious function for which the set of regular points is given here. And then I pass from function theory to to probability theory, and then we should recall the definition of the inverse function. So this is a function, monotone and continuous, and then its inverse function for the argument t is defined in this way. So this is the first time when the function crosses the level t, or this is a total time spent by this function below the level t, or this is the last time when this function crosses the level t. All three definitions are equivalent for monotone and continuous functions. But if it is not monotone, then the first crossing time and the last crossing time are different. There should be f to the minus 1 here in brackets. This is generalized inverse function defined in general for monotone and not necessarily continuous functions. This is the first time when, well, let's say the function exceeds the level t. Now, what is a relation to probability theory? We start with sums of random variables, independent, identically distributed, non-negative. This is crucial assumption. And then renewal process is defined in this way. So this is NT is generalized function for the sequence Sn. So we may write it in this way. More precisely, this is not generalized inverse function. This is almost generalized inverse function. Well, if the function is not monotone and non-continuous, you see this is the sum of lengths is a total time spent below the level. This is the last moment when it's below the level. This is the first time when it's above the level, and so on and so on. So these are three functionals important in applications and well studied in the literature. Well, I should speed up a little bit. So, dual functions, these are 2 f and g for which we can write something like this, and this is somehow inverse function, well, in a very general sense. For example, in number theory, if pi is a total number of primes less than x, and Pn is the nth prime number, then we have relation of this kind. And this shows that pi is somehow inverse function for p, for the sequence p, because pi of p of n equals n. By the way, if we interchange pi and p, we have no such a nice property. But this is generalized inverse in some sense. So this is indication. And general principle we follow in this book is that if we know that two functions are asymptotically equivalent, then we expect that their inverse functions are also equivalent, asymptotically equivalent. For example, in renewal theorem, so this is renewal theorem. If the first moment exists, then we have almost surely limit of this kind. And how to prove it? By using this general principle. So assume the sums behave like this. The mu is an expectation. I put it in the denominator. So general principle shows that inverses should behave in the same way. And now, inverse for this in n of t, renewal process, and inverse for the function mu times n is t over mu, and therefore we obtain renewal theorem. Just for free if we have a strong law of large numbers. The same in number theory. This is well-known prime number theory, describing the asymptotics of pi of x. It's x over log x. And then, so I write it in this way, showing that this function is asymptotically equivalent to this one. And then we expect that inverses have the same property, which means that nth prime number behaves like this. And this is just realization of the general idea. Well, for the third example, it's solutions of differential equations. So consider this Cauchy problem. And then one can show that the inverse for the solution is given by this formula. G is a function here. So this is inverse function. Therefore, x is the inverse of this integral. So this is proof of this result. So if we know the behavior of the integral, then we know the behavior of the solution. And this is really true, and we may even go further and consider stochastic differential equations which correspond to the previous one by letting sigma equals 0. And then we can investigate the asymptotic behavior of solution of stochastic differential equation. So in the last book, under the name of Buldygin, is sums whose terms are elements of linear random regression sequences. It was published 2014 by Runovska, nowadays Ilyenko, Marina, together with Buldygin. This is essentially all I wanted to tell you in this short talk. Thank you very much.